Hi, I'm Cindy Freud from Swansea University. I'm not talking too loud with the microphone, am I? I'll stand back a bit. And I'm just going to give you a brief introduction to the monitoring program that we had on the Lost Peatlands project before I pass over to the people who actually know the results of our monitoring program and can give us more detail, which is Joey Pickard and John Walker. So I think what we had here was a really unique, strong working partnership to deliver the monitoring for this project. And that, I think, was a key takeaway for me as a really good aspect of this project. So we worked together with the project ecologists and the university to really deliver a comprehensive monitoring program. So we had the monitoring, immediate monitoring of impact from our restoration activities that you would expect with standard best practice monitoring. But then we were able to focus in on some key scientific questions in more detail to really give us a better scientific basis for some of our key questions. And that was by being able to incorporate the university with more advanced equipment and methodologies to go more in depth on some of these questions. So I think we really built together, working together on our strengths and expertise and capacity to deliver a strong evidence-based program. So the results of this then will be able to inform ongoing management, to be able to help guide, hopefully, a future forest to bog restoration project, some best practice, and also to kind of look at some wider conservation objectives. So things like Pete was mentioning earlier about greenhouse gas monitoring. How can we use the results of this to inform wider policy and national level GHG greenhouse gas reporting. I think also, but by involving the university, so effectively what we did with the project ecologists was to firstly monitor pre-impact baseline conditions. So we have a baseline to assess our restoration activities, and then to monitor directly after the capital works project. So that sort of formed the basis of what you would have in a typical project monitoring, but by incorporating this project into our teaching and our research at the university, we'll be able to look at these results more long term. And I think it's important, again, that we emphasize the importance of these lost peatlands restoration sites. And I know others have mentioned this, but I just want to re-emphasize that these are really important. One of our big scientific gaps is in understanding afforested peatlands. So we need a lot more evidence from that. A lot of our evidence about afforested peatlands comes from Scotland. So again, a very different situation. People have already touched on that. Deeper peats, we're working with shallower peat here. And also, as people have mentioned previously, we're right on the edge of this range, this bioclimatic envelope for peatland development. And so I think it's really important to keep monitoring these sites into the future in the face of climate change to see how effective our restoration has been. So we took a three-pronged approach to monitoring. So first we had the core monitoring where we focused on hydrology, habitats, and species. And then some in-depth scientific investigations where we came up with the key questions during the development phase of the Lost Peatlands project. So we focused on vegetation change and microtopography, on total organic carbon and greenhouse gas emissions, so carbon dioxide and methane. And then we also kind of had an added value, I think, which the university could bring to the project, and that's that we effectively have this army of students out there. Okay, we have these students. They all have research projects to do, whether they're undergraduates, masters, PhDs. They want their projects to matter. They want to be able to provide useful information. But it's a bit difficult sometimes to harness that. So what we realized is by focusing student projects on key topic areas, we could get a lot more in-depth monitoring on some specific additional topic areas that we couldn't do in a standard project. So in terms of the core monitoring, what we really focused on was water table depth. So we've heard that discussed today, a key driver in these ecosystems. On broad scale vegetation change across the project sites, and on species, specifically bats, water voles, and birds. As I said then, we also looked at more in-depth at some topic areas, particularly microtopography and vegetation and carbon dynamics. And the reason we did this is it's not as simple as, okay, restore a peatland, reduce your carbon emissions. What we realize is that it's going to be more complex with that and vary over time. So we have a trajectory of change in terms of these carbon emissions. So for example, we go in, we do the restoration, there might be a pulse of carbon loss from that site. So whether through erosional processes, whether through dissolved organic carbon in the water being transported off-site. And what we want to know is, okay, how big are these pulses of carbon loss and how long does it last? How long till we get some recovery? Additionally, we have confounding factors. So if we're re-retting a site, restoring the peatland, reducing carbon emissions, we have other confounding factors in there. A big one that gets mentioned is we may be increasing methane emissions. So we want to monitor that as well. And I think one of the key findings we really had on this, and I don't want to take away from Joey's presentation in a minute where he'll go into detail, is it became really clear on the still forested site, so before any restoration happened, that there was a lot of methane being emitted from those drainage ditches, from the furrows. And I think we need to incorporate that into our understanding of these greenhouse gas dynamics. So as I said, Joey will be talking shortly and giving you some detail about the highlights of our monitoring results on this topic. And then we're going to pass over to John Walker, who's going to talk about the student projects and the sort of in-depth monitoring topics that they covered and what some of our key results were. Additionally, I think that what I found really important of this project was this concept of training the next generation of natural resource managers in Wales. So as an academic, I teach mainly on the master's program. I get a lot of students, showing up who have done, undergraduate degrees from all over the UK. Shockingly, very little knowledge of peatlands. I hate to say that, but it's true. And I think I really realized as we were going into this project. A lot of times on these projects, we talk about how, we need to educate the wider public about the value of peatlands. Well, we're training the next generation of ecologists, and we need to make sure that they understand the value of peatlands and all of the different ecosystem services involved in managing and restoring our peatlands. So we incorporated the Lost Peatlands project areas, so real world examples, of restoration in action that we could take students out to. We incorporated that into our lectures, into our university coursework, and I said for the field trips as well, to take them out. And I think this was really valuable to the students and made them appreciate not only peatland sites, but also just restoration design, and what we're doing in practical conservation. This was across departments, so biologists and geographers. And I think this was important because, as I said, maybe the students didn't come to us with a lot of knowledge about peatlands, but those that did also had significant gaps. So we might have had biosciences students, that already understood, okay, these are important ecosystems for their biodiversity, for the species and habitats they support, but literally no idea of what the physical makeup of a peatland is. So I take them out on the site, and say, you're standing, there's 2 meters of peat below you, and they just look in shock. To be honest, a lot of them had no idea about what the peat itself is, the structure of it. Alternatively, the geographers, and not to oversimplify, they might come and they're just viewing peatlands as a carbon store. And that's where their whole focus is. So I think beginning to make them realize all of the different value and ecosystem services that these sites hold. It was a really valuable aspect of this experience, incorporating the direct teaching at these sites. And also our international students. So we had a lot of students coming from tropical areas. So I think taking them up to the UK uplands and at peat bog in wind and cold wind, rainy conditions, it's something that they're not going to forget. So anyway, I will now pass over to Joey, who's going to give you some of the highlights of the main monitoring.
Cool. Thanks, Cindy. There's a few nervous faces out there. I'm going to tell you that it all worked, so don't worry. I'm Joey. I'm your friendly neighbourhood peatland ecologist, and I've emerged from the bog to take you through kind of our monitoring and evidence programme that we had internally at the council and working in partnership with Swansea University. It's a pleasure to be in a room full of people who already know where Neath, Talbot and Rhondda and Taff are and why they're important. But I've just put this map up because I want to talk about one specific feature, and that's the road that we all drive over to get to work every day. If you make your way from Hirwine down to Blaenrhondda or Treorchy, you'll go over the Rigos Road. This is the construction of the Rigos Road, cutting through metres and metres of peat. And in the same way that you get an accidental archive when you maybe press botanical specimens between old newspaper pages, you get a record of what was happening in the week that you took that flower from the field. The records that were gathered during kind of engineering exercises in the valleys give us a really good record of what the peatland looked like at that time, and also the impacts that that kind of engineering had on it. So this picture was taken in 1928, shortly after Richard started working for Rhondda Council. Yeah, getting in early. We identified quite early on that monitoring and evidence gathering was a really important part of our project. So it fit in really well with two of our kind of overall work programs, one focusing on restoration and direct management, and one which was focused on learning around what we were delivering and establishing best practice in Wales. We also identified really on that we had a real lack of understanding and evidence about what happens when you move from the conditioned state on the left to the one on the right. It's a quite intrusive process with a lot of changes that happen throughout the peat profile and on the surface. And we weren't entirely sure what the outcomes were going to be, or how best we could support kind of knowledge development. This is just a quick video, which is an animation of a 3D scan of one of our sites. This is what it looks like if you go there on day 0. So there's the drained and ploughed area of Craigan on the left, and we move over to the restored area, which was about 5 minutes after Cum left the area with the digger. And you can see the immediate changes of that drainage channel has been lost, the plough lines are completely gone, and you can see the water that's already being held up really high within the peat profile on the surface. We had kind of broad overarching objectives for our monitoring and evidence strategy. The first was to show that we were meeting our funding outcomes and we were doing what we said we would do. We had to focus on what could reasonably be observed within the lifespan of the project. So we had a years-long development and then a 4-year delivery. When you're talking about habitats that kind of take thousands of years to form, there are changes that can be observed in the short term, but it's also important that we had a real strong baseline for long-term monitoring. And we also had a program of ongoing monitoring for secondary changes as a result of kind of the wider scale habitat change, the changes in the bird, bat, invertebrate composition across the landscape. The challenges that we faced during the kind of development of the monitoring program was that the bioclimatic envelope that we sit in for these mountain blanket peatlands is really quite distinct from the areas where most of the evidence has been gathered within the UK. You can see the extent of the Fusnod flows. Up in the north of Scotland, we've got a warmer, milder climate. The peats tend to be a bit shallower, and compared to some of the stuff which you might get in other places of the country, it's a really kind of oceanic climate. So we were dealing with something quite unique and with the lack of evidence around it. The other challenges which we kind of faced day to day were just the joys of the Welsh weather, which this is a group of students who were maybe a bit less enthusiastic at the end of the day, going out to take some peat cores. To address the challenges, we really focused on kind of co-location of all our monitoring and evidence efforts to provide a kind of maximum efficiency. having everything centered around one area meant that we were able to monitor everything that would change in the short term and see which factors influenced each other. The partnership structure that we had meant that we were able to really effectively utilize those specialist expertise within the different institutions, and also we had access to some really special bits of kit which we wouldn't have been able to use if we didn't kind of have the partnership structure that we had. The benefit of working in the way that we did was that all of the partners had a really long-term view for what we needed to look at and how we needed to look at it, and the commitment from those partners meant that we had the confidence then to invest in this level of monitoring really early on. The priorities that we had for the project, I'm not going to go through all of the data that we gathered because I think we'll need to leave here at 4 and I'll probably still be talking about 10 at night, but we needed to focus on the immediate hydrological changes as a result of our restoration works, the changes in the vegetation and the Maya specialist communities, the kind of cascading changes on protected species and species of priority for conservation, and then focus on the carbon story of the peatland restoration that we do. So for the water table, ideally we wanted it to be higher, we wanted it to be more stable throughout the year. We want to see an expansion of Maya specialist species into areas of the sites that we didn't have them before. We didn't want to cause any kind of cascading loss of protected species as a result of the works. Ideally, we want to see a mass expansion of water voles and see them dancing across the habitat as we walk across. And then for the carbon side of the project, we didn't want to see a kind of mass spike in dissolved carbon leaving the site in the waterways after we've done our works. If I first look at hydrology, this is just another 3D scan of before and after of the habitat. You can kind of pick out the drainage channels and the plough lines, and on the other one you can see that they've been completely gone. This is what we talk about when we say microtopography. If you picture how the water would move through one of those habitat classes compared to the other, the pre-restoration works, everything sheets off really quickly into the drainage channels and plough lines and is taken away off-site. Once you remove those plough lines and create a bit more complexity within your kind of surface microstructure, it holds the water within the system for a lot longer, it's a lot rougher, there's less pathways for it to escape, and as the digger drives over it and compresses the peat, it also makes the rate of water infiltration into the soil a bit slower, and it holds the water table just that much higher. So we look at kind of specific responses of the hydrology to our restoration works. On the box plot on the left there, it's an unrestored versus a restored condition. So the base of the graph where it says 0 is ground level, and as you go up you're getting further away from ground level. So we want the box plots to be closer to the bottom of the graph. And that's what we observed after our restoration works. This is taken from our Castellnos HRA. The water table was higher. What we also found, which was something that we had to figure out as we went along, if you look at this graph on the right, the solid line is our pre-works water level, closeness to ground surface, and the dashed line is after. Ideally, you would want the dashed line to be further towards the left. That would mean the water table spends more time closer to the surface. And eagle-eyed among you will notice that it is not. So at first glance, it looked like the works had the opposite effect. It was only when we pulled in data from neighbouring sites and other conditions that we saw that it was actually just an effect of year-on-year changes in temperature. So this was quite a serious drought year. So we would have always had a lower water table than we would have expected at the start in a wetter baseline year. But by pulling in other data, we can see that actually that loss was less for us than it was for our neighbouring sites, and our restoration works have actually made that site more resilient to kind of climate extremes, which we're going to be dealing with more and more. Our vegetation data we went very intensive with, perhaps more intensive than some other restoration projects we would have seen. We had a network of quadrats over all of our sites where we recorded percentage cover of all our species on a 100-metre grid, so we ended up with about 350 quadrats, or about 100 per site. And then we did some really intensive work looking at how the vegetation structure changes with relation to the changes in microtopography that we see after. This is the data pulled out for the year-on-year changes in positive indicator species. Every year, for this site, this is Castellnos again, every year we had an increase in our numbers of positive indicator species found in our quadrats, and also the total percentage cover for our positive indicator species as well. So we've got more of the species that we want, and they cover more of our site than they did the previous year, every year. There are also some which appeared in quadrats for the first time after we'd done our restoration work. We had sundews and asphodel pop up in areas of the site which we didn't have before, and it's gone from something which was really quite degraded to one of the better condition areas of peatland in our project area. Protected species, we found new records for all of these across all of our sites, and that was something really special for us to have as a result of our works. Water vole, I'm going to go into a bit more detail in a minute. Adders, we found them on our Craigan restoration site, utilising an area which we didn't find them in during the baseline surveys after we did our works. And green tiger beetle, which was another one of our top 10 project species, moved into different areas of our habitats as well. So the water vole, when we first found them on Castellnos in 2021, were kind of limited to 2 areas in the north of the site. We didn't find them during our pre-restoration baseline surveys. It was something that we had to be quite reactive to, and it was a positive story, but did add a complication. So we went through our licensing exercises and then worked with the licensing team in NRW to come up with a strategy to mitigate any effects that there might be on water vole. When we started, the evidence base for the effect of upland peatland restoration on water vole population really wasn't there. And so this work, combined with the work that Gareth's been doing on PYC and work that Rob is doing as well with Inc., I think is probably one of the more effective data collection efforts that we've had. After the restoration works, they moved out into a wider area of the bog, which was really positive change. And then when we came to do our final portion of restoration on this site, they'd moved out even further, including into bits of the bog that we hadn't made it into yet. So the advice here and the lesson learned is that if you have water vole on your site, get in and restore as much of the site as possible in year 1, because they will exploit every available habitat niche that you make for them year on year. This is the total organic carbon readings. So it's probably the only screen big enough where you can see all of the bars along the bottom. That's weekly samples for about 18 months. And this is what we found. So total organic carbon is all of the carbon leaving through the watercourses coming off your site. And dissolved organic carbon is anything below a certain size threshold, so it's a filtered sample. The blue and orange is our restored site, and then the kind of maroon and lighter blue is our control site. And the laser pointer's not working, sorry. But the levels that we noticed up from our restored site never reached the levels of our control site, and also we didn't see that kind of massive spike that we were worried about leaving the site after our restoration works. So it was really positive. One thing we did learn about the kind of structure of the carbon leaving the watercourses of our site is that a higher percentage of the carbon export for the afforested site and the restored site was dissolved compared to the restoration site. So what that means is that for the restoration site, if you have 10 pieces of carbon leaving your site, 8 of them will be dissolved and 2 of them will be chunks of peat, compared to a control site where you might have just 10 pieces of dissolved carbon. So if we had known this earlier, and now we do, and we'd been able to put in kind of more intensive blockages into the streams to collect some of the pieces of peat as they wash away, we could have lessened our carbon export from that restoration site even more. So it's quite an important lesson for us to learn. A brief overview of how we measure greenhouse gas, because it's something that sometimes people aren't overly familiar with. So the kit on the right is the analyzer and the chamber. So the chamber sits on the soil and it sucks up the gas into it and it fires it through the analyzer, and then you get a reading for CO2 and methane at the end of it. Generally, the wetter your site is, the more methane you would expect, and the drier it is, the more carbon you would expect as a percentage of your total. The T3, T2, T1, and A2 and A1 are all relative levels of your micro-elevation within your peatland, and you can see the relationship between the amount of methane and the amount of carbon as you change your relative elevation of where you stand. So On the left of both of these box plots for carbon and methane is our restored site. The middle box plot is the afforested site, and the right-hand side is the control site. So we measured our carbon and methane expressed from the soil for those three habitat classes to see what the relationship was. And what we found was there was very little variation between the carbon emissions between each relative micro-elevation. But the highest carbon emissions were observed from the afforested site. Even in the period, this is just a subset of the data from last summer, but even in the period quite shortly after the restoration works, the amount of carbon coming from the restored site was actually lower than from the afforested site. For methane emissions, we had more methane coming from the restoration site, which is something that is expected. If you think about how things break down when they're in air compared to when they're in water, they would form carbon dioxide if they're able to connect to oxygen in the air, and if there's no oxygen available to them, they'll go through a different decay pathway and they'll make methane. When we do our restoration, which you saw in the videos earlier, you submerge all the vegetation that exists already on site below the water, so it can't decay to carbon dioxide, it's only got a pathway towards methane. Once that decay's finished, that methane pulse should go down. This is the importance of the long-term monitoring, as we can track this change long-term. The really interesting thing that we found from the methane monitoring is that the amount of methane coming from the drains in the afforested site was so much higher than the rest of that system that it was enough to push the total methane emissions to 3 times higher than the control site. Even though the average emissions across all micro-elevations might suggest that it's higher, the total emissions is greater from an afforested system where we are compared to the control system that we had. We did a lot of work with bioacoustics, and I'm not going to go through the specific responses we had from birds and bats and things. I'm just going to talk about it in generalities. These are before and after. So you can see no and yes of an unrestored and restored site of the total biodiversity that we picked up from one of our peatland restoration sites, and there was an increase in the total species usage of that site following the works. And then this is a chronosequence of sites from 1 year pre-restoration through the restoration year, and then up to 4 years after the restoration. And you can see there's a really good trend. There's an increase in everything that we have done so far. It seems to be working pretty well. That's everything from me, so I'm going to hand over to John.
Hi, I'm John Walker, a senior researcher at Swansea University. I'm just going to give you a very quick, brief overview of the supporting student projects that we've delivered in addition to the core monitoring that Joey's just been talking about. In total, we've initiated 21 student projects at Swansea University to help support and evidence the impact of the Lost Peatlands project. I say initiated because some of those projects are actually still ongoing, and hopefully most of those will report this year, or maybe even next year. But it's a very broad programme of evidence, and it's covered a whole range of academic kind of qualifications or levels of study at the university, which are presented in the table there, and covered undergraduates. But as you move down that table, obviously the duration and the complexity of those projects that those students have undertaken get greater, and I'm really pleased to see that we've got quite a lot of postgraduate studies, so quite kind of detailed projects that we've been able to deliver as part of this this work. I should say that on the right, that's Dunia, who in 2022 did her project on forest regeneration, conifer regeneration on restoration sites. I'm not sure why she's got her arms in the air when I took that photo. I don't know if it's in joy or frustration, or maybe she's just got her tape measure caught around something. This is the big table. This is just to communicate kind of the breadth of the topics and the focus of those 21 projects. I'm going to talk about the topics in the next slide, but and particularly on this slide, I wanted to just show that over the 6 years of the Lost Peatlands project, there's been 21 projects, but you can kind of see that obviously 2020, when we had the global pandemic, we didn't do any research projects at all. Students weren't allowed to do field work. And I think that probably had impacts on for the next year as well in terms of getting students out in 2022 because of uncertainty. And I kind of think that actually, if we hadn't have had a global pandemic, we'd probably have around 30 student projects would have been delivered towards the outcomes of the Lost Peatlands project. However, having said that, there's quite a lot of work to set up and to manage. There's lots of bureaucracy involved in the delivery of student projects, and I'd particularly like to thank Rahel Vattenfall and her colleague Lisa, and Gareth and Laura at NRW for all their support in the setup and the safe working conditions that we managed to kind of set up for the delivery of student projects across the Regos Mountains as part of this project. It's really invaluable and appreciated. So in total, what we've reported against as part of our reporting for the lottery-funded project is 9 sort of topic areas or work areas that students covered. Levels of heavy metals and the impact of restoration and forestry on peatland, the depth and structure of peat deposits and impact of forestry and restoration, the impact of or changes in peatland vegetation and impact of restoration and forestry. We've had we've reported 2 projects focused on peatland animals, peatland surface dwelling invertebrates and water voles, 2 projects looking at conifer regeneration on peatlands, 1 project looking at stormwater changes, post-felling of conifers, 1 project mapping catchments to inform where gully blocking activities could take place, a project looking at the factors affecting forestry success on peatlands, and finally a project looking at the distribution requirements of tree bryophytes in conifer plantations and broadleaf trees across the Regos Mountains. So there's a really broad programme, and they're in our final report as part of reporting. I'm just going to pick up on 3. I'm not going to go through 21 projects. I'm just going to pick out 3 example projects and just give some highlights and flavour about what the students have managed to do. This is Emily, who did an undergraduate's project in 2019. This was actually Emily's second attempt at a project. We tried to set one up in Banai Brachaniog, but we didn't collect any data. So she came to this project quite late and did a really good job. She worked really hard monitoring surface invertebrates, so peatland surface invertebrates, using pitfall traps, cups that are buried in the peat, and the surface dwelling invertebrates fell into those traps. She did 108 traps. She had 108 traps out of Castelnas, collected 447 invertebrates. And headline results that in the forested site she looked at was dominated by spiders, and in the intact site was dominated by crustacea and ants. Crustacea were all of the species, or all of the individuals that she collected were in the single genus Stygobromus. They look like that, tiny little kind of shrimp-like crustacea that are a couple of millimetres long that feed on decaying plant material. And then in the deforested site, which was actually a very old site where forestry hadn't been very successful, it was kind of transitional between these two states of forested and intact. But a really neat project and a really valuable data set that we wouldn't have had without Emily doing that particular piece of work. Donald, MSc student in 2023, his project partially looked at the heavy metal loadings, the pollution loadings within the peatlands along the Regos Mountains. He took metre-long peat cores, and for each 10 centimetre change in depth, he measured the amount of heavy metals. Using his data, I've managed to I've created these particular graphs, and I've just focused on 2 heavy metals, arsenic and lead. Heavy metals are spatially very variable in peatlands, and so what you need to do to be able to characterise heavy metal loadings within peatlands is take an awful lot of peat cores to reliably measure them. And whilst Donald took multiple measures, we also had another student, and that student is Jack, who's actually in that photograph there. Jack was an undergraduate student in 2019 who also took peat core samples, but his was an undergraduate project. He only did 40 centimetres depth because it's kind of more restricted in scope. But his data really verify Donald's data as well. They show the same patterns. And the patterns are that in untreed peatland, the dark blue, well, this is what they did. They compared untreed peatland with a forested and restored peatland, the light blue line on these graphs. So you've got depth and you've got the loading coming, increasing to the right of the slides. And what they both found was essentially this concentration, these very high levels of heavy metal loadings or contamination in the surface peat. Well, these surface peats down to about 20 centimetres kind of coincide with the heavy industry in the valleys of South Wales, below the Regos Mountains. So this pollution is probably a result of the heavy industry and the pollution that came out of all of those steel and coal works. Sorry. The very high levels that are found in the afforested, under the afforested peatlands, conifer trees, particularly conifers, are very good at filtering out atmospheric pollution, and they retain it in their leaves and in their structure, and obviously a good proportion of that ends up on the surface of the peatland, and so that's not unexpected. Again, Donald wasn't able to evidence the impact of those high heavy metal concentrations, or even the sources of them within the scope of his project. But what this does provide is some really, really valuable contextual information that we can use going forward to interpret the results that we find in terms of the land cover changes that take place on these peatlands kind of going forward. So, and again, another really valuable project and data set. Finally, for me, Kieran in 2021 looked at stormwater flows and the changes of stormwater flows on peatlands from a land cover change from being forested to being felled. And so this is our Cregan site that you've heard about. This is Cregan in 2016, fully covered in trees. 2018 is when the felling on that site started. It was completed by the start of 2019, but this is the site in 2020 and 2021. There's been no change. Shortly after this is when kind of the restoration works on that site started happening, but it was after Kieran's project. And very kindly, Andy Hood from Natural Resources Wales provided rainfall data in the blue and the discharge or water flow data, the black lines, from 2016 to 2022. And they were measured from this is a photograph of the water flow monitoring station that was located about here at the top of the Nant Cregan stream. And that stream was kind of the catchment for this southern area of this Cregan site, so this area here. So essentially those data monitor the transition from this state to this state, where there's lots of forestry brash, lots of rushes that have kind of become established on that site, but importantly it's before any kind of restoration actions on the site. And what Kieran did was he identified 150 storm events spanning across the period before and after felling to measure some key kind of metrics of storm flows. One, which are the peak levels of water which were leaving the catchment through this particular equipment, or what's called peak discharge. And what he found looking at the differences between the storms before and after the felling is that the highest levels of water were 9% lower post-felling. So the peak discharge was significantly lower post-felling after the removal of the trees. But he also looked at what was called lag time, which is the time between peak storm rainfall and the peak discharge, or the highest water levels leaving the catchment. That's called the lag time, which is a kind of measure of the speed of the water flowing over the land surface. And what he found, well, he found no overall significant difference in the lag times. But when he split those data seasonally to look at different seasons, he found that there were significantly longer lag times in autumn, but particularly in summer. And so in summer, he found that actually the water was flowing across that catchment far slower, in fact 60 minutes on average slower. So the transition from forestry to a felled state significantly slowed the flow of the water across that catchment to the edge of that peatland, which has quite significant potential impacts for downstream flood risk, probably caused by the increased surface roughness from the brash and the developing vegetation. There were Kieran's results as part of his MSc. It's been examined, but it hasn't been critically assessed. We really hope to repeat this work with up-to-date data after post-restoration works now, so we can include that phase for this particular site. But it gives a really strong, this is a really powerful student project based on NRW data that evidences kind of the ecosystem benefits of that transition from